Chapter 1. The Promise. On March 23, 1989, two electrochemists walked into a press conference at the University of Utah and announced that they had solved the world's energy problem. Not contained it, not improved it, solved it. Stanley Pons, chairman of the University of Utah's chemistry department, and Martin Fleischmann, one of the most respected electrochemists alive, stood before a crowded room of journalists and scientists and described an experiment so simple it could fit on a kitchen counter. Two electrodes submerged in heavy water, a small electrical current, and, they claimed, the unmistakable signature of nuclear fusion happening at room temperature. Cold fusion. Two words that contained inside them the promise of everything humanity had ever wanted from energy. Limitless, clean, cheap, safe. The fuel, a form of hydrogen extracted from ordinary water, existed in quantities so vast that the world's oceans could power civilization for billions of years. No carbon emissions, no radioactive waste, no geopolitical stranglehold over pipelines or oil fields, no wars over energy supply. Just an inexhaustible reaction occurring inside a jar of water on a laboratory bench. The press conference went around the world in hours. The New York Times ran it on the front page. Television networks led with it that evening. Politicians began drafting legislation to fund research. Scientists in dozens of countries dropped what they were doing and rushed to replicate the experiment. The stock market responded. Energy companies watched nervously. The phrase cold fusion entered the vocabulary of people who had never heard of electrochemistry. For approximately 5 weeks, it felt like the future had arrived early. And then, almost as quickly as it appeared, the dream began to unravel. Not with a single decisive refutation, not with a dramatic proof of fraud, but with something more ambiguous, more uncomfortable, and in many ways more interesting than either vindication or debunking. The cold fusion story collapsed under the weight of irreproducibility, institutional panic, and a scientific community that moved from cautious interest to outright rejection, faster than almost any episode in the history of modern science. But here is what makes cold fusion genuinely fascinating, and why it refuses to disappear despite more than 3 decades of official dismissal. Some researchers never stopped seeing anomalous results, not the dramatic claims of Pons and Fleischmann, not kilowatts of surplus energy pouring out of a glass jar, but something. Heat where there should be no heat. Traces of nuclear products where conventional physics says none can form. Small, reproducible, stubborn signals that refuse to be explained by ordinary chemistry and refuse to conform to the predictions of established nuclear theory. The story of cold fusion is not simply the story of a hoax, although hoax is the word most people reach for. It is the story of what happens when a credible scientific claim outpaces the institutions designed to evaluate it. When the machinery of peer review and replication encounters an effect that is real but inconsistent, when careers and reputations and funding structures collide with the possibility, however uncomfortable, that something genuinely strange might be happening inside a piece of metal soaked in heavy water. It is a story about ambition, about embarrassment, about the sociology of science, and about one of the most contentious and under-examined questions in modern physics: whether the anomalous heat observed in certain electrochemical experiments has a nuclear origin. Whether, somewhere buried beneath decades of controversy and institutional hostility, there is a real phenomenon waiting to be understood. If you are the kind of person who finds the intersection of energy, physics, and scientific controversy more compelling than any fictional drama, consider staying with this. The cold fusion story is more complicated than you have been told, more interesting than the official verdict admits, and more relevant to the present moment than most people realize. Get comfortable. This one goes deep. Chapter 2. The Science Before the Storm. To understand what Pons and Fleischmann claimed in 1989, you need to understand what nuclear fusion actually is and why achieving it had been one of the central obsessions of physics for 4 decades before that press conference. Nuclear fusion is the process by which 2 light atomic nuclei combine to form a heavier nucleus, releasing enormous quantities of energy in the process. It is the same reaction that powers the Sun. In the Sun's core, where temperatures reach approximately 15 million degrees Celsius and pressures are unimaginable by terrestrial standards, hydrogen nuclei, protons, are forced close enough together that the strong nuclear force, which operates only at extremely short ranges, can overcome the electromagnetic repulsion between the positively charged particles and bind them together. The result is helium, and the energy released in the process is what makes the Sun shine. The energy released per unit of fuel in a fusion reaction is extraordinary. A single kilogram of deuterium fuel, the form of hydrogen most commonly discussed for fusion reactions, contains the energy equivalent of roughly 10 million kilograms of coal. There is no combustion, no carbon dioxide, no long-lived radioactive waste. The primary reaction products are helium and, in some fuel combinations, neutrons. Helium is inert and harmless. The neutron flux from certain reactions does require management, but it represents nothing like the multi-generational hazard posed by the waste products of nuclear fission. The challenge, which physicists and engineers had been battling since the 1950s, is reproducing the conditions that make fusion possible. Those conditions are extreme by any measure. To bring hydrogen nuclei close enough for the strong force to operate, you must first overcome the Coulomb barrier, the electromagnetic repulsion between 2 positively charged protons or deuterium nuclei. Doing this requires either enormous kinetic energy, which means temperature, or enormous pressure, or some combination of both. In practical terms, achieving controlled fusion requires sustaining a plasma, a superheated gas of ionized hydrogen nuclei, at temperatures exceeding 100 million degrees Celsius. That is roughly 7 times hotter than the core of the Sun, because the Sun compensates for relatively lower temperatures with crushing gravitational pressure unavailable in any terrestrial device. At those temperatures, no material vessel can contain the plasma directly. It must be held in place by intense magnetic fields or crushed inward by powerful lasers in an approach called inertial confinement. The tokamak, the dominant magnetic confinement design, threads the plasma through a donut-shaped magnetic field configuration, preventing it from touching the reactor walls. Building tokamaks capable of sustained fusion has occupied some of the finest minds in physics and engineering since the 1950s. The ITER reactor in southern France, a collaboration of 35 nations representing more than half the world's population, is currently the largest and most expensive fusion experiment ever attempted. As of 2026, it has not yet achieved its first plasma experiments. The broader history of magnetic confinement fusion is a story of extraordinary technical achievement and perpetual postponement, always approaching the threshold of net energy gain, always finding new technical obstacles to surmount before the goal is reached. Laser-based inertial confinement fusion, the approach pursued at the National Ignition Facility in California, achieved a historic milestone in December 2022 when it produced more fusion energy than the laser energy delivered to the fuel target. It was the first demonstration of fusion ignition in a laboratory setting, a genuine scientific achievement. What it did not produce was more energy than the total electrical energy consumed by the facility to drive the lasers. That gap remains substantial. The path from scientific demonstration to a functioning power plant remains long. This is the context in which cold fusion appeared. Mainstream hot fusion, despite billions of dollars and decades of effort by thousands of the world's best physicists and engineers, had not yet produced a sustained net energy gain. The joke commonly repeated in fusion research circles was that commercial fusion power had been 20 years away for the past 60 years. And then 2 electrochemists claimed to have achieved it in a jar. Martin Fleischmann was not a fringe figure. He was a Fellow of the Royal Society, one of the most distinguished scientific honours Britain confers. His work on electrochemistry, particularly in the field of surface-enhanced Raman spectroscopy, was widely respected. He had spent 30 years studying the behaviour of molecules and currents at electrode surfaces. He was not the kind of scientist who made reckless claims. Stanley Pons was his former graduate student, now a department chair. Their collaboration was genuine, their credentials substantial, and their claim, at the moment they made it, rested on experimental data they had been collecting in secret for several years. What they had observed was this. When a palladium electrode was placed in heavy water, which contains deuterium rather than ordinary hydrogen, and a small electrical current was passed through the system in a process called electrolysis, something happened inside the metal that could not be explained by ordinary chemistry. The palladium appeared to produce more heat than the electrical energy being put into the system. The excess heat, they argued, could only come from a nuclear reaction, specifically from deuterium nuclei fusing inside the palladium lattice. Their explanation proposed that palladium, which has an extraordinary ability to absorb hydrogen, was loading deuterium into its crystalline structure at such high density that the nuclei were being forced close enough together for fusion to occur. Not hot fusion in a superheated plasma. Cold fusion, catalyzed by the metal's atomic lattice, occurring at room temperature with no magnetic confinement, no lasers, no extreme engineering. The theoretical basis for this was, to put it gently, thin. Conventional quantum mechanics calculations predicted that the probability of 2 deuterium nuclei tunneling through the Coulomb barrier at the energy levels available in a room temperature system was so vanishingly small as to be effectively impossible. The numbers were off by many orders of magnitude. Nuclear physicists who looked at the claim were almost universally skeptical from the start. But Pons and Fleischmann had data. They had been measuring what appeared to be a sustained excess heat signal for years. They were cautious enough to want more time before publishing. What they did not count on was being scooped. Chapter 3. The worst press conference in science. The story of why the cold fusion announcement happened the way it did is itself a cautionary tale about the pressures that operate on scientists and institutions in moments of perceived discovery. In early 1989, Fleischmann and Pons learned that another researcher, Stephen Jones, at nearby Brigham Young University, was working on a similar electrochemical approach to nuclear fusion. Jones was pursuing what he called piezo-nuclear fusion, looking for small quantities of fusion products in electrolytic cells rather than the dramatic energy output, that Fleischmann and Pons believed they had found. The two groups were not in competition in quite the way the media later portrayed, but the prospect of being anticipated drove events in a direction that would prove catastrophic. University administrators, sensing the enormous financial and reputational implications of a genuine energy discovery, pressured Pons and Fleischmann to announce before Jones could publish. Patent filings needed to be established. Priority needed to be claimed. The announcement was scheduled for March 23, 1989, before the researchers felt fully prepared and before the work had been submitted to peer review. This is the first critical structural failure in the cold fusion story, and understanding it matters. The announcement was not made through normal scientific channels. It was not preceded by publication in a peer-reviewed journal where other experts could evaluate the methodology and data before the public heard the claim. It was made at a press conference before the science had been vetted, driven by institutional concerns about intellectual property rather than by scientific readiness. The result was that the global scientific community heard about one of the most extraordinary claims in the history of physics through newspaper headlines. They were given partial information, incomplete methodology, and no access to the primary data. They were expected to evaluate a claim of nuclear fusion occurring in a laboratory jar, based on a press release and a conference presentation that omitted crucial details about the experimental setup. The ensuing chaos was, in retrospect, almost inevitable. Within days of the announcement, laboratories around the world began attempting to replicate the experiment. Teams at MIT, Caltech, Stanford, Georgia Tech, Oak Ridge National Laboratory, and dozens of universities in Europe and Asia all tried to reproduce the effect. The early results were deeply mixed. Some groups reported seeing excess heat. Others saw nothing. Some thought they detected neutrons, a signature product of certain fusion reactions. Others detected nothing above background. The problem was that nobody knew exactly what Pons and Fleischmann had actually done. Critical details of their experimental protocol, the specific type of palladium used, the preparation procedure for the electrodes, the exact current densities, the precise conditions under which excess heat appeared had not been published. When laboratories attempted replication, they were guessing at parameters that turned out to be crucially important. Pons and Fleischmann, meanwhile, were besieged. The University of Utah held press conferences before peer review. The Utah State Legislature voted funding for a cold fusion research institute. Members of Congress introduced bills. The pressure to perform, to demonstrate, to defend came from every direction simultaneously. In this environment, mistakes were made. A crucial error emerged regarding neutron measurements. Pons and Fleischmann had reported detecting neutrons at levels consistent with a fusion reaction, but a basic calculation showed that if the neutron flux they claimed were real, they would both have died of radiation poisoning within days of exposure. The number was wrong by a factor of approximately 1 billion. When this was pointed out, the response was not a clear acknowledgement of error and correction. It was confusion and qualification and retreat, which damaged credibility far more than a straightforward admission of mistake would have. By May 1989, less than 2 months after the announcement, the consensus in the mainstream physics community had shifted decisively against cold fusion. A workshop held by the Department of Energy concluded that the existing evidence did not support the claim of cold fusion and did not merit major federal investment. The phrase cold fusion became shorthand for scientific embarrassment. But here is where the story becomes more complicated than the simple narrative of debunked pseudoscience. The vote at that DOE workshop was not unanimous, and the experiments did not stop. Chapter 4. What actually happened in the labs? The public story of cold fusion, the one that settled into mainstream discourse over the decade following 1989, is that every serious attempt at replication failed. That the excess heat Pons and Fleischmann reported was an artifact of bad calorimetry, a measurement error, a chimera produced by the wishful thinking of researchers who had convinced themselves they were seeing something that was not there. This narrative is comforting because it is clean. It resolves the dissonance. It allows the scientific community to move on with its understanding of nuclear physics intact. It is also incomplete. The more careful version of history acknowledges that the replication situation in 1989 was far murkier than the clean story admits. Several respected laboratories did observe excess heat in electrochemical experiments with palladium and heavy water. The effect was real in the sense that thermometers registered energy output exceeding electrical input. What it was not in those early experiments was consistently reproducible on demand. The excess heat appeared in some cells under some conditions and not in others that seemed identical. This inconsistency was maddening and ultimately fatal to the initial wave of research, because science requires reproducibility as its most basic criterion. But inconsistency is not the same as non-existence. And the researchers who remained in the field after the mainstream exodus believed they knew why the results were erratic. The palladium was the key. And the palladium, it turned out, was extraordinarily difficult to control. Palladium is a rare platinum group metal with an unusual property. It can absorb hydrogen atoms into its crystalline lattice at densities approaching 1 hydrogen atom per palladium atom. This loading ratio, expressed as the ratio of hydrogen to palladium atoms in the metal, turned out to be critical. Experiments suggested that the anomalous heat effects appeared only when loading ratios exceeded approximately 0.9, meaning 9 hydrogen atoms for Moses every 10 palladium atoms. Below that threshold, nothing anomalous occurred. The problem is that achieving and sustaining high loading ratios is technically demanding and highly sensitive to factors that are difficult to control. The purity of the palladium, the crystalline structure of the electrode, the surface preparation, the current density, the temperature, the electrolyte composition, the presence of trace impurities that could either help or hinder loading. All of these variables interact in ways that are not fully understood even now. Different batches of palladium from different suppliers behaved completely differently. A protocol that worked brilliantly in one laboratory failed entirely when transferred to another, not because anyone was doing anything wrong, but because the material itself was not standardized. This was the dirty secret beneath the replication failure of 1989. Laboratories attempting to reproduce the Pons and Fleischmann experiment were not, in most cases, actually reproducing the experiment. They were guessing at critical variables with palladium of unknown and variable quality, using protocols based on incomplete descriptions, and then declaring failure when results did not appear. The failures were real, but they were failures of replication under poorly controlled conditions, not necessarily failures of the underlying phenomenon. The most significant early evidence that something real was occurring came not from excess heat measurements but from the detection of anomalous nuclear products, particularly a helium isotope called helium-4, in experiments that showed excess heat. If the excess heat were a nuclear effect, the question became what reaction was producing it. Standard deuterium fusion produces two roughly equal branches of products, a helium-3 nucleus plus a neutron or a tritium nucleus plus a proton. If either of these reactions were occurring at rates sufficient to produce the observed heat, the neutron or proton fluxes should be easily detectable. They were not, at least not at the expected levels. But a third possible fusion path does exist. Two deuterium nuclei can fuse to produce helium-4 plus a gamma ray. This path is exceedingly rare in conventional hot fusion, constituting less than 1 part in a million of standard fusion reactions. But it produces no neutrons. It produces helium-4. Starting in the early 1990s, a small number of researchers began measuring helium-4 in experimental cells that showed excess heat. The correlation was striking. Cells that produced excess heat accumulated helium-4. Cells that produced no excess heat accumulated no helium-4. And the ratio of excess heat to helium-4 production was, in several experiments, close to what would be expected if the reaction were deuterium plus deuterium going to helium-4 plus energy. The clearest demonstration of this correlation came from work at the Naval Research Laboratory, where researchers, including Melvin Miles, measured both heat and helium simultaneously in 21 experiments. Heat and helium appeared together. Their absence also correlated. The probability of the correlation being accidental was estimated at less than 1 in 1,000. This was not the result of a fringe laboratory. This was government-funded research at a respected federal institution, published in peer-reviewed journals. It did not receive significant media attention, partly because the cold fusion story had already been written, and partly because the results were anomalous enough to resist easy interpretation. But it remained in the scientific literature. It did not go away. The defense establishment, it turned out, had reasons of its own to take the anomalous heat observations seriously. Several national laboratories, including Oak Ridge, the Naval Research Laboratory, and the China Lake Naval Air Weapons Station, maintained research programs in what the field had begun calling condensed matter nuclear science, a term deliberately chosen to avoid the radioactive connotations of cold fusion. The work continued quietly, outside the mainstream, dismissed by most physicists, but never quite abandoned by the small community that had observed results they could not explain and were determined to understand. Chapter 5. The Men Who Would Not Stop. Science is supposed to be self-correcting. When a claim fails the test of replication, the claim is abandoned, the researchers move on, and the field advances. This is the process that works. This is why science produces reliable knowledge, where other human enterprises produce ideology and superstition. But self-correction requires that the correction actually happen, that the reasons for failure be correctly identified, and that the question of whether the failure reflects the absence of a phenomenon or merely inadequate methods be honestly examined rather than assumed. In the case of cold fusion, the self-correction happened too fast, driven by institutional pressures, reputational concerns, and the embarrassment of a scientific community that had made the mistake of taking the claims seriously before the evidence warranted it. The researchers who continued working in the field after the mainstream exodus were not, for the most part, cranks or wishful thinkers. They were people who had seen results in their own laboratories that they could not dismiss, and who believed the scientific process required investigating those results, rather than ignoring them because they were inconvenient. Among the most significant was Yoshiaki Arata, a Japanese physicist of considerable standing who had made substantial contributions to plasma physics before turning his attention to cold fusion. Arata developed a technique using palladium nanoparticles rather than bulk electrodes, reasoning that the increased surface area and different structural properties of nanoscale metal might produce more consistent results. His experiments, reported over many years, produced what he described as consistent excess heat and helium production. His status in Japan insulated him from some of the professional costs that Western researchers in the field faced. Stanislaw Szpak and Pamela Mosia-Boss at the Space and Naval Warfare Systems Center in San Diego spent years developing increasingly sophisticated experimental protocols for electrochemical cold fusion. Their work, published in peer-reviewed journals, documented not only excess heat, but what appeared to be localized nuclear reactions on palladium electrode surfaces, detected through a technique called CR39 solid-state nuclear track detection. CR39 is the same polymer used in some safety glasses. When charged nuclear particles pass through it, they leave distinctive tracks that can be counted and analyzed. The tracks Szpak and Mosia-Boss observed in their experiments were consistent with what would be expected from nuclear reactions occurring on the electrode surface. Their work was controversial. Critics argued that the tracks could have been produced by chemical contamination or background radiation. But the statistical analysis was careful, the control experiments were included, and the results were reproducible in their laboratory. This was not a single experiment reported once. It was a sustained research program producing consistent results. Edmund Storms, a former Los Alamos National Laboratory chemist, spent decades after his retirement carefully measuring and documenting excess heat in cold fusion experiments. His work produced a compendium of data from hundreds of experiments across dozens of laboratories worldwide, showing the consistent correlation of certain experimental conditions with anomalous heat. Storms's contribution was not flashy new results, but careful collation of existing data, demonstrating that the effect, whatever its cause, had been observed too many times by too many different researchers in too many different countries to be entirely explained by measurement error. The cumulative body of work from these researchers and others like them was not nothing. By the mid-2000s, several hundred papers on the subject had been published in peer-reviewed journals. The data included excess heat measurements with highly sensitive calorimetry, detection of helium-4 correlated with heat, CR39 track detection suggesting charged nuclear particles, low-level tritium production in some experiments, transmutation of elements in electrode surfaces suggesting nuclear reactions of some kind, and highly localized heat production on electrode surfaces that could not be explained by ordinary chemical processes. None of this constituted proof of the specific mechanism Pons and Fleischmann had proposed. None of it demonstrated the kind of robust, on-demand reproducibility that would satisfy the standards of mainstream physics. But it was not nothing. And the scientific community's treatment of this body of evidence, primarily ignoring it, occasionally attacking it, rarely engaging it with the rigor it would have applied to results in any other field, was itself a significant failure. The sociology of cold fusion rejection is as interesting as the physics. To work in cold fusion was to risk one's career. Young researchers who expressed interest in the field were warned by senior colleagues. Grant applications mentioning the subject were rejected without review at many funding agencies. Papers submitted to mainstream physics journals were often returned without peer review on the grounds that the subject was outside legitimate science. The field of cold fusion had been placed in a special category of preemptively excluded claims, a category that is itself a violation of scientific practice. Science is not supposed to have forbidden questions. This created a perverse feedback loop. The best equipped laboratories, with the best calibration equipment and the most rigorous protocols, were precisely the laboratories where researchers could least afford the professional risk of doing cold fusion experiments. The work therefore tended to migrate to smaller programs, to researchers nearing or past retirement, to national laboratories where program managers had idiosyncratic tolerance for unconventional research. This was not an environment designed to produce the decisive, reproducible, impeccable experimental results that would have been required to force the mainstream to reconsider. The exile of cold fusion from mainstream science ensured that the mystery at its heart remained unresolved. Chapter 6. The second evaluation. In 2004, 15 years after the original DOE report had effectively buried cold fusion as a legitimate research area, the Department of Energy conducted a second review. This time, the context was different. A new body of experimental evidence had accumulated. Researchers with data asked for a fresh look. The DOE assembled a panel of scientists to evaluate submissions from cold fusion researchers, including experimental data, theoretical proposals, and summaries of the accumulated body of work. The results of the review were published in 2004, and they were more ambiguous than the 1989 verdict. The panel was evenly divided. Some reviewers found the evidence for anomalous heat effects in deuterium-palladium systems credible enough to warrant further investigation. Others did not. The majority recommended that funding agencies should be open to evaluating well-designed experiments on a case-by-case basis, rather than the blanket exclusion that had characterized the preceding 15 years. This was not an endorsement of cold fusion. It was not a reversal of the dominant scientific consensus. But it was a meaningful shift in the official posture from active dismissal to cautious agnosticism. And it generated almost no public attention. The second DOE review was not reported by the New York Times. It did not generate television segments. The science journalists who had covered the original story with such excitement in 1989 had moved on. Cold fusion was still radioactive in the reputational sense, and the nuanced conclusion of a second government review was not the kind of story that competed successfully for attention in a media landscape increasingly driven by drama and clarity. The researchers in the field noticed, but the general public did not, and so the field continued in its strange twilight state, pursued by a small dedicated community, ignored by the mainstream, generating data that refused to fit either the true believer's grand narrative of unlimited clean energy or the skeptic's clean verdict of complete debunking. The theoretical situation remained deeply unsatisfying. If anomalous heat and helium-4 were real, what was producing them? The conventional nuclear physics explanation was impossible by several orders of magnitude. The Coulomb barrier between two deuterium nuclei at room temperature should prevent fusion with overwhelming certainty. The theoretical framework that works for hot fusion in plasmas, where particles have high kinetic energies distributed across Maxwell-Boltzmann statistics, did not provide any mechanism for fusion at the energy scales available in an electrochemical cell. But several alternative theoretical frameworks were proposed, none of them fully satisfying, all of them struggling with the same problem of explaining how nuclear reactions could occur in a condensed matter environment at energies far below the Coulomb barrier. One class of proposals invoked collective quantum mechanical effects in the metal lattice. The argument was that in a highly loaded palladium lattice, deuterium nuclei might behave as a collective quantum system rather than as individual isolated particles. In collective quantum states, the effective barrier for tunneling might be substantially different from the single particle calculation. This was not proven, but it was not obviously wrong either. Condensed matter physics is full of emergent collective phenomena that cannot be predicted from single particle behavior. Another class of proposals focused on the possibility that the environment inside a metal lattice could modify nuclear reaction rates through mechanisms not present in vacuum or plasma. The coupling between electromagnetic fields in the lattice and nuclear dynamics was proposed as a potential mechanism. Some calculations suggested this coupling could be significant, though the magnitudes required to explain the observed excess heat were many orders of magnitude larger than any calculated value. A third approach looked at the role of muons, exotic particles that can substitute for electrons in hydrogen atoms. Muon-catalyzed fusion, in which a muon replaces an electron in a hydrogen molecule to create a much smaller and denser structure, where nuclear distances are reduced by the muon's much smaller orbit, was a well-established phenomenon, first observed in the 1950s. Muons can catalyze hundreds of fusion reactions before they decay. This was not cold fusion in the Pons and Fleischmann sense, but it demonstrated that nuclear fusion could occur at subthermal energies under the right conditions. Some researchers speculated that mechanisms analogous to muon catalysis might operate in metal lattices, though no viable candidate mechanism was identified. None of these theories produced quantitative predictions that matched observations well enough to constitute a convincing explanation. The field remained and remains in a peculiar state of empirical suggestiveness without theoretical foundation, which is the most uncomfortable place a scientific claim can occupy. Chapter 7. Energy and Urgency. To understand why cold fusion refused to die, despite 3 decades of official dismissal, you have to understand the energy context in which it existed. The late 1980s were not the first time humanity had confronted the implications of finite fossil fuel supplies and environmental damage from combustion. But the specificity of the threat was becoming clearer. Carbon dioxide concentrations in the atmosphere were rising measurably. Climate models were producing projections that, while uncertain in their details, were increasingly consistent in their general direction. The energy problem was not just an economic or geopolitical concern. It was becoming an existential one. The promise embedded in cold fusion, whether or not it was achievable, was precisely calibrated to meet that threat. An energy source that used seawater as fuel, produced no carbon dioxide, generated no long-lived radioactive waste, and could in principle be implemented in distributed installations rather than requiring the centralized infrastructure of conventional power generation, was the answer to the energy problem in nearly every dimension that mattered. This is why the claim generated such extraordinary excitement in 1989. This is why it was embraced before the evidence was in. And this is why, even after the mainstream rejection, some researchers and some institutions continued to pursue it. The potential reward was not just a scientific discovery. It was the solution to the most consequential technological challenge the civilization faced. As climate change became more urgent through the 1990s and 2000s, as renewable energy began developing but revealed its own challenges in intermittency and storage, as hot fusion continued to advance tantalizingly but remained perpetually decades from commercialization, the appeal of cold fusion, understood as the possibility of a dense, clean, simple energy source achievable without extreme conditions, did not diminish. If anything, it grew. The energy situation as of 2026 illustrates why. Renewable electricity generation has expanded dramatically. Solar and wind power now constitute significant fractions of electricity generation in many countries. Battery storage technology has improved substantially and costs have fallen. But the deep decarbonization of the economy, including heavy industry, long-haul transportation, aviation, shipping, and high-temperature industrial processes, remains a formidable challenge. The difficulty of replacing fossil fuels in these sectors with existing clean energy technologies is real and not easily dismissed. In this context, a dense, clean energy source that could provide high-temperature heat, as well as electricity, that could operate continuously without dependence on weather or geography, that could scale from small to large installations, would be transformative in ways that go beyond what even a complete build-out of solar, wind, and conventional nuclear fission can provide. The problem is not that renewable energy is insufficient in principle. The problem is that the transition is slow, expensive, and politically contested, and the climate does not wait. The urgency of that context is part of why cold fusion never fully disappeared from serious attention, even as it disappeared from mainstream scientific discourse. Chapter 8. LENR. The rebranding. By the early 2000s, the researchers who had remained in the field had largely abandoned the term cold fusion. It was too contaminated, too strongly associated with the press conference debacle of 1989, too reliably triggering of dismissal and ridicule. A new term emerged to describe the broader class of phenomena they were studying. Low-energy nuclear reactions, or LENR. The name was chosen deliberately. It made no claim about the specific mechanism. It did not invoke the discredited language of cold fusion. It described what was being observed, anomalous nuclear effects in condensed matter systems at energy scales far below those associated with conventional nuclear physics, without presuming to know what was causing them. It was a scientific name for a scientific mystery. The rebranding helped somewhat. Papers published under the LENR label had slightly better odds of surviving initial screening at peer-reviewed journals. Conference proceedings accumulated. A small but serious community of researchers continued to publish, share data, and refine their methods. The LENR community had developed, by the 2000s, a fairly clear picture of what conditions seemed to favor the anomalous effects. Loading ratio was critical, as noted earlier. High surface-to-volume ratios in nanostructured materials seemed to help. Certain additives to the electrolyte, particularly lithium compounds, appeared to enhance effects in some experimental protocols. The phenomenon was associated specifically with deuterium, not ordinary hydrogen, in most but not all experiments. And the effects seemed to appear only after significant loading time, often requiring days of electrolysis before any anomalous heat was observed. These were not the observations of researchers inventing effects from wishful thinking. They were systematic, empirical findings about the conditions that appeared to favor an anomalous phenomenon. The pattern was consistent enough that experienced researchers in the field developed intuitions about when experiments were likely to succeed or fail. Intuitions grounded in hundreds of accumulated experimental observations. But the field had a serious credibility problem that went beyond the original 1989 debacle. Several high-profile claims within the LENR community turned out to be wrong or fraudulent or simply too extraordinary to survive careful scrutiny. The most damaging was the case of Randell Mills and his company Blacklight Power, which claimed to have discovered a form of hydrogen chemistry, not nuclear physics, that produced large amounts of energy. Mills's claims attracted investor funding and generated media attention while producing no independently verified power device after decades of effort. Blacklight Power, later renamed Brilliant Light Power, remained as of the mid-2020s a company with proprietary claims and no publicly demonstrated technology. More damaging still was the case of Andrea Rossi, an Italian inventor who in 2011 began publicly claiming to have a working cold fusion device he called the energy catalyzer, or ECAT. Rossi claimed extraordinary energy output from nickel powder and hydrogen in the presence of a secret catalyst. He staged dramatic public demonstrations that generated enormous media coverage and attracted significant attention from people eager to believe. Early demonstrations appeared to show excess energy, but they were never conducted under conditions that excluded the possibility of fraud or hidden energy inputs. Subsequent independent tests produced contradictory results. Legal disputes followed. By the early 2020s, Rossi had become the defining symbol of LENR charlatanism for skeptics, and the damage to the field's reputation was real and significant. These episodes illustrate a structural problem that legitimate LENR research has never fully solved. The field exists in a space where it attracts, almost magnetically, both sincere researchers pursuing genuine anomalies and fraudsters who recognize that LENR claims are difficult to definitively refute, and therefore provide useful cover for schemes targeting credulous investors and institutions. Separating the two categories requires exactly the kind of rigorous independent evaluation that the field's semi-excluded status from mainstream science makes difficult to obtain. The legitimate researchers in the field are acutely aware of this problem. The cumulative effect of the Rossi episode and similar cases on the credibility of genuine work has been devastating. When a serious electrochemist publishes careful data showing anomalous heat in a palladium-deuterium experiment, they are now evaluated in the shadow of a long history of extraordinary claims, implausible devices, and disappointed investors. The prior probability assigned to any LENR result by mainstream reviewers is extremely low, not because the specific evidence is without merit, but because the category has been so thoroughly contaminated by bad actors. This is not fair. But science is practiced by humans in human institutions, and human institutions respond to track records and associations as well as to specific evidence. The fair response to this situation would be rigorous independent evaluation of the most compelling LENR research, separated from the fraudulent claims and evaluated on its own merits. That response has been slow to materialize. Chapter 9. Toyota, Mitsubishi, and the Japanese investment. One of the most underreported aspects of the cold fusion story is the sustained interest of major Japanese corporations and research institutions in the phenomenon after 1989. Japan has a specific national context that makes this interest comprehensible. It is a country with essentially no domestic fossil fuel resources. Its economy depends entirely on imported oil, natural gas, and coal. The 2011 Fukushima disaster caused a dramatic reassessment of nuclear fission's role in the energy mix, leading to the shutdown of most of the country's nuclear fleet and a sharp increase in energy costs and carbon emissions as replaced by fossil fuel imports. Energy security and energy cost are live national concerns in a way they are not in countries with abundant domestic resources. In this context, Toyota Motor Corporation funded significant cold fusion research through its research institute in the 1990s, publishing results that confirmed excess heat and helium-4 correlation in some experimental conditions. Mitsubishi. Heavy Industries conducted research on nuclear transmutation in metal lattices, observing apparent element transmutations in palladium exposed to deuterium that could not be explained by any conventional chemistry. These were not fringe institutions. Toyota and Mitsubishi are serious companies with serious technical capabilities. The Mitsubishi transmutation results were particularly intriguing. When certain elements were deposited on the surface of palladium and the system was exposed to deuterium flux, the deposited elements appeared to transmute to neighboring elements in the periodic table, as if they had absorbed one or more deuterium nuclei. The results were reproducible in the Mitsubishi laboratory and were later replicated by a team at the Toyota Research Institute. The transmutations were slow and produced small quantities of product, not the dramatic energy release of the Pons and Fleischmann claims. But they were real in the sense that mass spectrometry could detect the transmuted elements. Transmutation in a condensed matter system at room temperature was, by any conventional understanding of nuclear physics, impossible. And yet it appeared to be happening. The Toyota and Mitsubishi results were published in peer-reviewed journals and remain in the scientific literature without adequate explanation. The Japanese government's funding agency, NEDO, also supported research programs in what it called New Hydrogen Energy, a category that included LENR research. This was a small program by the standards of major energy research initiatives, but its existence demonstrated that the Japanese scientific establishment did not simply dismiss the phenomena the way the American and European mainstreams did. The contrast with American science policy is instructive. In the United States, the DOE's 1989 verdict effectively closed the door on federal funding for cold fusion research for 15 years. Individual national laboratories could and did pursue the work, sometimes semi-covertly, but there was no sustained federal program. The second DOE review in 2004 recommended openness to evaluating individual proposals, but did not create funding mechanisms. As of 2026, there is still no major federal cold fusion or LENR research program in the United States. In Japan, the calculation was different. The downside risk of spending a few $1 million on research that might confirm an impossible phenomenon was small. The upside risk of dismissing a real phenomenon that could solve the national energy problem was enormous. The asymmetry of those risks justified continued investigation even without theoretical clarity. Chapter 10. What NASA actually said. In 2011, a video appeared on the NASA website that surprised many people who thought they understood the cold fusion story. Dennis Bushnell, chief scientist at NASA Langley Research Center, referred to LENR as potentially the most important energy innovation in human history. He described anomalous heat experiments in metal hydrogen systems as potentially representing a real physical phenomenon with very significant energy output. He noted that if LENR were real, the implications for terrestrial energy and space propulsion would be transformative. This was not a fringe opinion from a junior researcher. This was the chief scientist at one of the most prestigious aerospace research centers in the world. And he was not saying LENR was proven. He was saying it was real enough to warrant serious investigation. NASA Langley had conducted its own internal research on the phenomenon and had seen results that the chief scientist found compelling enough to discuss publicly. The video did not generate significant mainstream media coverage. Cold fusion had been dead for 20 years in the public imagination, and the rebranding as LENR had not penetrated general awareness. But in the small community following the field, Bushnell's statement was significant evidence that serious technical people in serious institutions were taking the anomalous effects seriously, not because they were credulous, but because they had seen data that they could not dismiss. NASA was not alone among aerospace and defense organizations in taking interest. The Defense Advanced Research Projects Agency, DARPA, had funded several small LENR research programs at various points. The Naval Research Laboratory, as described earlier, had conducted sustained research for years. The European research community included researchers at major institutions who had observed anomalous effects. None of this translated into the sustained, well-funded, institutionally supported research program that the phenomenon would need to be definitively resolved. The structural problem remained. The mainstream scientific community had rendered a verdict in 1989, and overturning that verdict required the kind of unambiguous, reproducible, peer-reviewed evidence that was extremely difficult to produce in an environment where the best-equipped laboratories were reluctant to risk their reputations on the question. The result was a permanent state of inconclusive inquiry, sustained by a small dedicated community, producing intriguing but not definitive results, generating just enough anomalous data to prevent complete dismissal, but not enough to force mainstream reconsideration. Chapter 11. The private sector arrives. The past decade has brought something new to the cold fusion and LENR landscape. Serious private sector investment from people with both significant technical sophistication and no professional stake in the mainstream physics consensus. The entry of private capital into unconventional energy research is itself a reflection of the urgency of the climate situation and the growing frustration in some quarters with the pace of mainstream clean energy development. Venture capitalists who had made fortunes in information technology and biotechnology began looking at energy with different eyes, asking whether the same willingness to fund long-shot technically difficult bets that had paid off in other fields might produce comparable returns in energy. Most of the private LENR investment has remained quiet for understandable reasons. The stigma is real. Companies do not advertise investments in cold fusion. But enough information has become public to suggest that the total level of private interest in the field is substantially larger than the public footprint would suggest. Google's Advanced Technology and Projects Group funded a multi-year research program specifically aimed at understanding whether LENR phenomena were real, published in the journal Nature in 2019. The results were mixed, finding no clear evidence of the anomalous heat effect under the conditions studied, but the research identified technical areas where further investigation was warranted and concluded that the question was not definitively resolved. Google committed to continued investigation. The significance of the Google research was not primarily the results, which were not dramatically positive. It was the institutional legitimacy the investment implied. When a major technology company with substantial scientific resources decides to investigate a claim that the scientific mainstream had dismissed, it signals that the claim has not been settled to the satisfaction of all serious technical observers. Several other technology companies have reportedly funded LENR research at various scales. Some startups have formed specifically to pursue the technology, with varying degrees of public disclosure. The climate of secrecy around many of these efforts reflects both the commercial sensitivity of potentially valuable intellectual property and the professional risks that still attach to association with cold fusion. The most interesting development in the private sector has been the application of modern materials, science and nanotechnology to the experimental conditions. The original Pons and Fleischmann experiments used bulk palladium electrodes. Modern LENR research is applying techniques from semiconductor fabrication, nanoparticle synthesis, surface science, and advanced materials characterization that were simply not available in 1989. Researchers are using engineered nanostructures with precisely controlled compositions and geometries, applying advanced diagnostics that can measure phenomena at the atomic and molecular scale, and using computational modeling to predict which material configurations might favor the anomalous effects. This is a different kind of research from the original electrochemical experiments. It is more systematic, more controlled, more informed by modern materials science, and more capable of distinguishing between chemical and nuclear explanations for observed effects. Whether it will produce the decisive results that the field has lacked for 35 years remains to be seen. Chapter 12. The Theoretical Wilderness. The greatest unsolved problem in cold fusion research is not experimental, it is theoretical. The experimental situation, however frustrating in its inconsistency, has at least produced a substantial body of data over 35 years. Heat measurements by sensitive calorimetry, nuclear product detection by mass spectrometry, and particle detection. Transmutation evidence by isotopic analysis. The data, taken as a whole, presents a picture of something anomalous happening in certain metal hydrogen and metal deuterium systems under certain conditions. The theoretical situation is worse. There is no satisfying explanation for what that anomalous something might be. The proposals that have been offered range from the marginally plausible to the wildly speculative, and none of them has produced quantitative predictions that match the experimental observations with the precision that would be required to constitute a real theory. The problem starts with the Coulomb barrier. In free space, two deuterium nuclei cannot fuse at room temperature because the probability of quantum mechanical tunneling through the electromagnetic repulsion barrier between them is astronomically small. The Gamow factor, which quantifies this tunneling probability, produces numbers so small that the expected fusion rate in a palladium lattice, calculated from first principles, is effectively zero on any observable timescale. But condensed matter physics knows that first principles calculations from single particle quantum mechanics do not always work in complex many-body systems. The history of condensed matter physics is a history of emergent phenomena that could not have been predicted from the behavior of individual particles. Superconductivity, the complete absence of electrical resistance in certain materials below a critical temperature, was an inexplicable mystery for decades after its experimental discovery, before a theoretical explanation in terms of collective electron behavior was worked out. The quantum Hall effect, the superfluidity of helium, topological insulators, high-temperature superconductivity in copper oxide ceramics. All of these represent phenomena where the many-body physics of condensed matter produces effects that are not present in and could not have been predicted from simple calculations. Some theoretical physicists have argued that cold fusion might represent another such emergent phenomenon. The condensed matter environment of a highly loaded palladium lattice is genuinely exotic. The deuterium nuclei inside the metal are not free particles in vacuum. They are quantum mechanical objects embedded in a crystalline environment that screens, modifies, and couples to their electromagnetic interactions in ways that might, in principle, alter the effective barrier they must overcome to interact. The coupling between nuclear degrees of freedom and the collective electronic states of the metal, normally negligible in ordinary circumstances, might become significant in a highly loaded system operating far from equilibrium. These arguments have not produced a working theory, but they identify the right place to look. A convincing theoretical explanation for anomalous nuclear effects in condensed matter would need to demonstrate a specific mechanism by which the collective properties of the metal lattice could enhance nuclear reaction rates by many orders of magnitude, from effectively zero to rates that could produce observable heat. It would need to explain why the effect is specific to deuterium and not ordinary hydrogen in most experiments. It would need to explain why the dominant product appears to be helium-4 rather than the more common branches of deuterium fusion. And it would need to do all this from a theoretical foundation consistent with existing quantum mechanics and nuclear physics. That is a very difficult problem. It has not been solved, and it will not be solved by researchers who are not taken seriously enough to receive adequate resources and institutional support. The theoretical emptiness of the field is not merely an academic inconvenience. It is the primary reason why mainstream physics continues to resist engagement with the experimental results. In physics, an anomalous result without a theoretical mechanism is treated with deep suspicion. The history of science includes many cases where apparently anomalous results turned out to reflect experimental errors, systematic biases, or confounded variables, rather than real physical effects. The prior probability assigned to a claimed phenomenon is strongly influenced by whether any plausible mechanism can be identified. For cold fusion, the absence of any mechanism consistent with known physics has meant that every anomalous result is assumed by mainstream reviewers to reflect experimental error rather than a real effect. This assumption is not irrational given the state of the theory, but it is also not obviously correct, and it has the practical effect of making the field very difficult to evaluate fairly. Chapter 13. The problem of reproducibility. At the heart of everything wrong with the cold fusion saga is the reproducibility problem, and understanding it properly requires distinguishing between two very different types of irreproducibility. The first type is total irreproducibility. The original experiment fails in every attempt at replication, in every laboratory, under every condition. This is the strongest evidence that a claimed effect is not real. It is what the mainstream verdict on cold fusion in 1989 claimed had happened. The second type is conditional irreproducibility. The experiment sometimes works and sometimes does not, in a manner that is not yet understood. The effect is real, but it depends on conditions that have not been fully characterized. This type of irreproducibility is common in the early stages of research into genuinely novel phenomena, particularly in condensed matter physics, where material preparation and experimental conditions can have dramatic effects on outcome. The cold fusion situation is clearly the second type, not the first. Results have been reproduced across multiple laboratories by multiple independent groups using multiple different experimental approaches. They have not been reproduced reliably or on demand. But the occurrence of anomalous effects is documented far too broadly across the literature to represent total irreproducibility. The distinction matters because total irreproducibility supports a verdict of false claim, while conditional irreproducibility supports a verdict of poorly understood phenomenon requiring further investigation. These are very different conclusions, and the cold fusion discourse has consistently conflated them. What would it take to achieve consistent reproducibility? Based on the accumulated experimental literature, several factors seem critical. Material quality and preparation are paramount. The palladium or other host metal must be of high purity, and the loading process must achieve and sustain high deuterium to palladium ratios. Both conditions require careful control. The protocol must be followed precisely and consistently. Small deviations in current density, temperature, or electrolyte composition can apparently make the difference between active and inactive cells. Modern materials. Science has tools that were not available in 1989 for characterizing and controlling these variables. Electron microscopy can reveal the grain structure of metal electrodes at atomic resolution. X-ray diffraction can measure loading ratios in real time. Advanced surface preparation techniques can ensure consistent electrode quality. If the anomalous effects are real and depend on material conditions, modern techniques should be able to identify and control those conditions more precisely than the original experiments could. This is the argument for a properly resourced, institutionally supported research program aimed specifically at achieving consistent reproducibility. Not the scattered, underfunded efforts of the past 35 years, but a systematic, well-equipped campaign to characterize the phenomenon well enough to understand when and why it appears. Such a program would cost millions rather than billions, and its failure would at least definitively answer the question. Its success would be transformative. No such program has yet been funded. Chapter 14. What if it is real? Let us engage seriously with the question that the cold fusion story ultimately demands. What if the anomalous effects are real? What if there is genuinely a process occurring in condensed matter systems where nuclear reactions at low energies produce heat and helium-4? What would that mean? The energy implications are the most obvious starting point. If the effect can be scaled and controlled, the fuel source is effectively unlimited. Deuterium is present in ordinary water at a concentration of about 1 part in 6,000 by molecular ratio. The oceans contain approximately 45 trillion tons of deuterium. If a significant fraction of that could be converted to energy through LENR reactions, the resulting energy supply would last billions of years at current global consumption rates. The supply constraint that haunts every other energy technology, including uranium for nuclear fission and even the rare materials required for some renewable energy equipment, would effectively disappear. The environmental profile would be extraordinary. The only reaction product in the helium-4 producing pathway would be helium, an inert noble gas already present in the atmosphere. No carbon dioxide, no nitrogen oxides, no sulfur compounds, no particulates, no long-lived radioactive waste. The radiation produced by the reactions themselves appears, based on existing experimental data, to be highly suppressed compared to what conventional hot fusion physics would predict. If true, this reduces the shielding requirements dramatically compared to conventional nuclear technologies. The distributed nature of the technology would be transformative for energy access. Unlike large nuclear plants or coal-fired stations, a LENR-based energy device, if it could be realized, would not inherently require large-scale centralized infrastructure. It might be deployable at scales from individual buildings to industrial facilities to transportation systems. The implications for energy access in developing countries, for remote communities currently dependent on diesel generation, and for the economics of energy-intensive industries are difficult to overstate. The implications for climate change are potentially decisive. If a clean, dense energy source were available at acceptable cost, the economic argument for continuing to use fossil fuels would collapse. Every industrial process, every transportation system, every heating and cooling application currently powered by combustion could in principle transition to LENR-derived energy. The speed of that transition would depend on technology development and manufacturing scale-up. But the fundamental obstacle, the difficulty of making clean energy competitive with cheap fossil fuels, would be resolved. Space exploration is another domain where a validated LENR technology would be significant. The mass and complexity of carrying fusion fuel for propulsion has been a major challenge for proposed fusion-powered spacecraft concepts. If nuclear energy could be extracted from hydrogen or deuterium in a condensed matter system without the extreme conditions required for hot fusion, the possibilities for spacecraft propulsion would expand considerably. These implications are worth stating clearly, not because they constitute evidence that the effect is real, but because they explain why the question deserves rigorous investigation rather than dismissal. The potential consequences of the effect being real are so large that the cost of continuing to ignore it if it turns out to be genuine is almost unimaginable. The cost of investigating it rigorously and finding it does not exist is modest by comparison. This is the asymmetry that justified Japanese corporate investment in the 1990s, that motivates private sector interest in the 2020s, and that should, in principle, justify a serious publicly funded research program. Chapter 15. 2026, where it stands. As of 2026, the cold fusion story occupies an uncomfortable and unstable position. On one side, the mainstream scientific consensus remains dismissive. The term cold fusion is still radioactive in the reputational sense. Most physics departments will not fund research on the subject. Most peer-reviewed physics journals will not publish papers using the term. The careers of researchers who commit to the field remain at risk. On the other side, the anomalous experimental results continue to accumulate. The helium-4 correlation with excess heat has been confirmed in multiple independent laboratories. The nuclear transmutation results from Mitsubishi have been replicated. The CR39 track detection results from the Naval Research have been partially replicated. The excess heat effects, while inconsistent, have been observed far too broadly to be dismissed as systematic measurement error. The private sector investment in LENR research is quietly growing. Several companies are pursuing the technology without public disclosure. The Google research program published initial results and committed to continued investigation. Several national laboratories maintain small research programs. The Japanese government and private sector continue to support research. The theoretical situation remains unresolved. no satisfying mechanism has been identified. Several theoretical proposals exist, all of them speculative, none of them producing precise quantitative predictions. The critical need, which has been the critical need for 35 years, is for a properly resourced, institutionally serious research program aimed specifically at definitively resolving the reproducibility question. Not a small academic exercise, not a covert national laboratory program. A serious, well-equipped, independently evaluated research effort with the mandate and resources to characterize the experimental conditions thoroughly enough to achieve consistent results if they are achievable, and to conclude definitively that no effect exists if consistent results cannot be achieved under carefully controlled conditions. The cost of such a program would be small relative to its potential significance. $100 million sustained over 5 to 10 years with access to modern materials, science facilities, and participation from researchers in nuclear physics, condensed matter physics, and electrochemistry would be sufficient to definitively answer the question that has been inadequately answered for 35 years. The question is not whether cold fusion or LENR is real in the sense of already being proven. The question is whether the body of evidence is compelling enough to warrant the investment required to find out. And by any serious accounting, the answer is yes. The downside of finding that the effect is not real is a research program that fails to produce a revolutionary energy technology. That is a significant cost, but it is not catastrophic. The scientific community invests in uncertain bets routinely. The downside of continuing to ignore the evidence is the possibility of having overlooked the most important energy discovery in human history, because it was embarrassing. That is a much larger cost. And given the climate urgency of 2026, the timeline for figuring this out is not indefinite. Chapter 16. The Forgotten Breakthrough. Here is what we actually know, stripped of both the true believer's enthusiasm and the mainstream's dismissiveness. We know that Pons and Fleischmann made claims in 1989 that were premature, inadequately supported, and communicated through channels that bypass the normal processes of scientific evaluation. That is true. We know that many of the specific claims made in 1989 were wrong. The neutron flux numbers were wrong. The original calorimetry was flawed. The theoretical justification was non-existent. That is true. We know that the immediate replication attempts in 1989 were chaotic, conducted with inadequate information about critical experimental parameters, using materials of variable and uncharacterized quality. That is true. We also know that excess heat has been observed in palladium-deuterium electrolysis experiments by dozens of research groups over 35 years. We know that helium-4, a nuclear product that cannot be explained by chemistry, correlates with excess heat in multiple independent experiments. We know that nuclear transmutation effects have been observed in metal deuterium systems and partially replicated by independent groups. We know that researchers at serious institutions, including national laboratories, major corporations, and universities around the world, have observed anomalous effects that they could not explain by conventional chemistry. We know that the theoretical framework for explaining these effects does not exist. We know that the mainstream physics community, having rendered a verdict in 1989, has largely declined to seriously revisit the question. We know that the professional and institutional costs of working in the field have systematically prevented the best-equipped researchers from doing so. And we know that the world badly needs a clean, dense, scalable energy source, and that the existing technologies, however impressive in their development, have not yet solved the deep decarbonization problem. What we do not know is whether the anomalous effects observed in condensed matter nuclear systems represent a genuine new physical phenomenon or a persistent, systematic experimental artifact. That question has not been definitively answered, and it has not been definitively answered not because the answer is obviously negative, but because the question has not been given the serious, adequately resourced investigation it deserves. The cold fusion story is not, as it is usually told, the story of a hoax. It is not the story of two credulous scientists who fooled themselves and embarrassed science. It is a more complicated and more interesting story than that. It is the story of a premature announcement that contaminated a legitimate scientific question, of an institutional overreaction that foreclosed serious investigation before it could be conducted, of a small dedicated research community that kept working despite professional exile and produced results that the mainstream has never adequately explained, of a theoretical crisis that has no satisfying resolution, of an energy problem so urgent that it demands we revisit every lead, however uncomfortable. And it is, perhaps, the story of a discovery that may still be waiting to be made. The electrochemical cells on the laboratory benches in 1989 were crude. The palladium was uncharacterized. The protocols were inconsistent. The calorimetry was imperfect. The theoretical framework was missing. The announcement was premature and the subsequent chaos was predictable. But something was happening inside those cells, small, inconsistent, poorly understood, tantalizing in its correlation with nuclear products, stubbornly present in data from laboratories too numerous and too independent to dismiss. What that something is, whether it represents the beginning of a new field of physics, a misunderstood surface chemistry effect, or something else entirely, is a question that 35 years of inadequate investigation have not answered. The nearest star is 4.24 light-years away. It may be beyond our reach for centuries, but the anomalous heat in a palladium electrode might be reachable with a serious program, a clear experimental protocol, and the courage to ask a question that science declared dead before it was fully examined. The universe has not changed its mind about whether the effect is real. We simply have not asked clearly enough to hear the answer. Go outside tonight. Look at the lights in the windows around you, the electricity that powers them, the infrastructure that produces and distributes it, the fossil fuels that generated most of it, the carbon dioxide that combustion added to the air. Consider what it would mean if the answer to that problem had been sitting, misunderstood and dismissed in a laboratory jar since 1989. Then consider that we do not actually know it was not. That uncertainty is the real legacy of cold fusion. Not a hoax, not a proven miracle. A question we abandoned before we answered it. A mystery we declared solved when what we meant was inconvenient. The forgotten breakthrough may not have been a breakthrough at all, but it may have been the door to one. And 35 years later, with more urgency than ever, we still have not looked carefully enough behind it. That is not a comfortable place to end, but it is where the evidence leaves us. And the evidence, as uncomfortable as it sometimes is all we have.